Now let us go to analyzing heat conduction within objects that we cannot consider as heat or slump systems. Here again is a picture of that steak that we discussed at the beginning of this module. Notice that although the top surface of the steak may still look raw, the bottom surface on the other hand already looks well cooked once we turn the steak over. The reason behind this is that the heat coming from the frying pan does not diffuse as fast as we want it to throughout the entire thickness of the steak. This therefore creates a relatively large temperature gradient between the bottom and the top surfaces of the steak. The image in the right shows how the heat inside the steak diffuses through time. Therefore, this image shows us that in transient heat conduction, the temperature of a certain point inside an object is a function of two parameters. First is its position relative to a reference point, and second is time. Recall that this is the one-dimensional transient heat conduction when there is no heat generation inside an object. Solving this requires non-dimensionalizing the parameters that we see in this equation. When we non-dimensionalize time in this equation, the heat transfer parameter that we obtained is called the Fourier number, which is denoted by Fo or the Greek letter tau. It is computed by dividing the product of the thermal diffusivity of the object and the duration of time of the heat conduction process by the square of the characteristic length of the geometry. Now, the characteristic length during transient heat conduction is quite different for some geometries compared to the characteristic length of these geometries when we consider them as lumped systems. For plane walls with a thickness of 2L, the length or the characteristic length is still equal to half of its thickness. But for both long cylinders and spheres with a radius of r sub O, the characteristic length is now equal to the radius of these geometries. Now that we know how to compute for the Fourier number, we must now investigate what its physical significance is. Remember that the thermal diffusivity alpha can be written as the ratio of the thermal conductivity of the object to the product of its density and specific heat. Then, to simplify the form of the equation further, let us just replace the characteristic length L sub c by the notation L to designate one of the dimensions inside the body. Now we can multiply L to both the numerator and denominator, thereby resulting to this form of the equation. But we can place time in the numerator to the denominator of rho times c sub e times L cubed, which will then transform the equation in this way. Next, we know that the length L in the numerator can be found by dividing L squared by L. Finally, by multiplying the temperature change delta T to both the numerator and denominator, we can transform the formula for Fourier's number in this way. We can see in this transformed formula that Fourier's number just represents the ratio of the heat conduction through an object with a cross-sectional area L squared and a thickness L to the rate of heat storage inside an object with a volume L cubed.